G'day. I found this old transistor tester in my pile of junk. I've got no idea whether it works. This looks like it's aged a bit and a bit of corrosion on the screen printed front panel. The kit was originally described by a silicon chip. And the kit itself was put together by Dick Smith Electronics. There's a part number there that looks pretty hard to read. There's a simple on-off switch and a couple of LEDs with a screen printed legend of what fault or whether the transistors are any good or not, and some 3 leads coming out with some nice little small clips. So what we might do is in this episode clean it up a bit, pull it apart and see if we can get it to work, put it back together I mean. Going by the weight, I think the battery is still in there, so not having played around with this for more than 20 years, I suspect the battery would be corroded somewhat, so there may be some damage from that, but we'll see how we go. Silicon chip, I don't have the original instructions for this anymore, but the magazine silicon chip is still going strongly in Australia, and on their website I was able to find the original article, and I had to fork out $10 for a electronic copy of the magazine for the year that this was made. Doesn't actually have the date on here. I'll find that out in a minute. I think it was like 1993. It was in the 90s anyway. So this is the original article that I've printed out, and it gives a complete rundown of how it works. The circuit diagram, parts list, component layout, the artwork for the front panel, and the etching pattern for the PC board. Gives the construction details and how to go about using it for testing transistors. So firstly, I think we'll open it up and just have a look and see what's happened to that battery inside there. Okay, looks like I've stuck a bit of paper in there at some stage, a bit of cardboard to stop the battery shorting out on the circuit board. So the battery hasn't corroded at all, so that's good. It looks nice and clean inside. No doubt that battery will be dead. So the PCB is pretty much held in place on the front panel by these LED bezels, which is probably okay. There's not much weight to it or anything, and it should be well. So what I might do is take this away and just clean it up in my other workshop, see if I can make it a little bit more respectable looking. Then we'll stick a new battery in and give it a go. Okay, well that cleaned up quite nicely, just with a bit of spray and wipe. So let's just put a new battery in and see if we can get something to happen. I'll reuse that little bit of cardboard there. Seem to have done the trick. The cables come out. Probably better get the order right, because we won't know where to connect them if we don't. Just like that. Line up one of these cables. There's just little notches cut out in the plastic case to seat those cables, those wires, I should say. Okay, and according to the instructions, with no transistors tested, when we turn it on, both LEDs should flash. And look at that. So let's find a couple of transistors lying around and give it a little test. Okay, I've got 3 transistors here to test. This one here is a MJE 350 power transistor. And so I'll hook that up. The red one is for the emitter. I think that's the emitter here. The brown wire is for the base. This one. And the last one, the black wire, is for the collector. So we'll turn that on. And in this case, the LED flashes indicating that this is a PNP type. And there's no collector emitter short and no base emitter short. So that transistor is a go, which is I expected. It's an unused transistor straight out of my parts kit. And it is in fact a PNP transistor. Alright, the next one here is a BC546, a small signal transistor, and I have looked up the pin out. So the emitter is this one on the right. The collector is the one on the left. And the base is in the middle. Let's see what happens with this one. Look at that. This one's a goer as well. Just one LED flashing, signifying it's an NPN transistor, which indeed it is. Once again, there's no shorts. So that's a pretty simple test really for these. It doesn't show you any other information about the transistor. Let's do one more. Little metal can transistor. This one is quite old. BC177. There's a little notch on these to indicate what goes where. And in this case, the emitter is the one closest to the tab. The next one around is the base. And then obviously the collector is the last one. Once again, we've got a good transistor there. It's flashing, indicating a PNP transistor with no shorts. I don't really have any transistors that are faulty, so I can't really show you that. So it's a nice, neat little piece of test gear for you to have lying around. If I was to remake this, I would probably put some grommets or something for the cable entry into the project box. And instead of this 7-core hookup wire, I would use a flexible test lead type of wire. So let's have a little look and see how this circuit actually works. Alright, there's not much to the circuit diagram. There's a couple of transistors, capacitors, resistors, and the 2 LEDs, and this little diode network down here, and the 3 cables out, one for the emitter, one for base, one for collector. The original documentation refers to the TUT, T-U-T, for transistor under test. So the transistor circuit here consists of 2 BC548 NPN transistors configured in a standard Astable Multivibrator. The oscillation frequency is set to about 5 Hz via these resistors and capacitors here. 100k resistor and 1 microfarad capacitors. So we end up getting a 5 Hz square wave at the collector of this transistor, and a 5 Hz wave at the collector of this transistor in the opposite phase. So this transistor is driving the emitter of our transistor under test, and the other transistor is driving the collector via the diode array here. The LEDs are connected in reverse parallel. And because the 5 Hz output signals on the collectors of these transistors are complementary, the voltage levels will be out of phase. So when one is high, the other is low. This is going to cause the LEDs to flash alternately with the power applied when no transistor under test is connected. Frequency is a little bit fast to be able to see that they're actually flashing alternatively. So we'll have to just trust that that's what's happening there. Now when we connect a NPN, the article describes 2 conditions to consider, and the first is when the collector of Q1 is low and the other collector is therefore high. The NPN connected here will be biased on, and so there will be current flow through D3 and D4. And which also means there's be about 1.2 volts across D3 and D4, which is too low to keep the second LED on. So the LED 2 goes out when the test transistor is conducting, and LED will also be off because it is reverse biased at this point. So when the phase is reversed and the Q1 collector goes high, Q2 collector will be low. The transistor becomes biased off, and so LED 1 will be on, and LED 2 becomes reverse biased and remains off. And so that means if it's a working NPN transistor, LED 1 flashes while LED 2 stays off at all times. LED 1 being the one on the left here, and that is the one that indicates an NPN transistor. Now when you're testing a PNP, the opposite pretty much occurs. Q1 when that is low and Q2 collector is high, the transistor under test is biased off and LED 2 is lit. While LED 1 is reverse biased in this case and remains off. So when the collectors change state, the transistor under test becomes biased on, and so current flows through diodes 1 and 2, so through here. And so in this case, because of the voltage across the two diodes, both LEDs will remain off, one being reverse biased and one because of the saturation voltage of the transistor and the voltage drop across the diodes doesn't allow the transistor to bias on. Yeah, but that's okay. So that's for two working transistors. Now let's imagine that we've connected a transistor with a collector emitter short. It doesn't matter if it's an NPN or a PNP device. Neither LED will light because the current will flow through alternately each of the series diodes for each reverse of phase, and so that 1.2 volts across those LEDs is insufficient to bias the transistor on in either case. Now, if the bias, if there's a base emitter short on the transistor under test, then the transistor becomes unable to turn on, and current flows through that 1K base resistor. And in this case, the both LEDs remain alternately flashing with the 5 Hz pulse. Because the 1K resistor is sufficient to allow the LEDs to operate rather than through that diode network with that voltage drop. Alright, so I think I've got that more or less sussed out. Probably confused most of you, or there'll be people screaming at their screens saying, no, that's not how it works, but near enough. So yeah, once again, there we have it, 1993 designed transistor tester from Silicon Chip, Australian Electronics Magazine. A nice short and sweet episode for you this episode. We'll catch you on the next one. Cheerio.